The high current draw in the good phases of 26 and 29 amps is likely due to several factors. Firstly, consider voltage drop. The long distance of 1500 feet and the high power demand of 9600 watts of the circuit can cause a significant voltage drop over the line. As the voltage drops, the lamps will draw more current to maintain their operating power. Secondly, inductive load is another factor. High-pressure sodium lamps are inductive loads, which means they draw current in a lagging phase. This causes the current to peak later than the voltage, resulting in a higher current draw. Thirdly, line loss also plays a role. The resistance of the long line can also contribute to line loss, requiring high current to deliver the same power to the lamps. Now, addressing the bad phase lag, it could contribute to the high current draw if it is causing an unbalanced load. When one phase is not delivering power, the other two phases must carry the entire load. This can lead to an increase in current draw in those two phases. Regarding overcurrent protection sizing, the original overcurrent protection was likely sized at 40 amps to provide protection against overloads and short circuits. It may have also been oversized to account for potential voltage drop and inductive load characteristics. To address the current draw and ensure proper operation of the light pole, consider the following recommendations. 1. Investigate voltage drop. Check the voltage at the light pole to determine the extent of the voltage drop. If significant, consider using a larger conductor size or voltage regulation devices. 2. Inspect lamp ballasts. Ensure that the lamp ballasts are functioning properly. Faulty ballasts can cause higher than normal current draw. 3. Repair bad phase lag. Locate and repair the fault in the bad phase lag to rebalance the load and reduce current draw on the good phases. 4. Consider power factor correction. Install power factor correction capacitors to improve the power factor and reduce current draw. Let's delve deeper into each of these aspects. When examining voltage drop, it's important to understand that conductors have resistance. The longer the conductor, the greater the resistance. And the higher the current, the greater the voltage drop. This relationship is defined by Ohm's law: voltage equals current times resistance. In a long run like 1500 feet, even a small resistance per foot of the conductor can add up to a significant total resistance. Using a larger conductor size will reduce the resistance, and thus reduce the voltage drop. Alternatively, voltage regulation devices such as buck-boost transformers can be used to compensate for the voltage drop by boosting the voltage at the load end. When inspecting lamp ballasts, understand that ballasts regulate the current to the lamp and provide the necessary starting voltage. A failing ballast can draw excessive current or provide an incorrect voltage, leading to inefficient operation or even lamp failure. It's important to check the ballast voltage and current ratings against the lamp specifications to ensure proper operation. Use a multimeter to measure the voltage and current of the ballast and compare these readings to the manufacturer's specifications. When repairing the bad phase lag, understand that a break in the conductor or a high resistance connection can prevent the flow of current. This can be caused by corrosion, loose connections, or physical damage to the cable. Locating the fault often involves using a cable fault locator, which sends a signal down the cable and detects the point where the signal is interrupted. Once the fault is located, the cable can be repaired or replaced. When considering power factor correction, understand that the power factor is the ratio of real power to apparent power. Inductive loads like HBS lamps draw reactive power, which does not contribute to useful work, but increases the current flowing in the circuit. This increases the voltage drop and line losses. Power factor correction capacitors provide reactive power, which cancels out the reactive power drawn by the inductive loads. This improves the power factor, reduces the current draw, and reduces the voltage drop and line losses. The size of the capacitor required depends on the amount of reactive power drawn by the inductive loads. This can be calculated using the power factor of the load and the apparent power. Now let's talk about the 40 amp overcurrent protection that's in place. Overcurrent protection devices such as circuit breakers and fuses are designed to protect conductors and equipment from overloads and short circuits. The size of the overcurrent protection device should be based on the ampacity of the conductor, which is the maximum current that the conductor can safely carry. The National Electrical Code, NEC, provides tables that list the ampacity of different conductor sizes and types. The overcurrent protection device should be sized no larger than the ampacity of the conductor. However, in some cases, it may be necessary to oversize the overcurrent protection device to allow for motor starting currents or other temporary overloads. In the case of the high mast light pole, the overcurrent protection device may have been oversized to account for the inrush current of the HPS lamps when they are first turned on. Inrush current can be several times the normal operating current of the lamp. It is also important to consider the voltage drop when sizing the overcurrent protection device. If the voltage drop is excessive, the lamps may not start or operate properly. In this case, it may be necessary to increase the conductor size or install a voltage regulator. So, in summary, the high current draw in the good phases is likely due to a combination of voltage drop, inductive load, and line loss. Bad phase light can also contribute to the high current draw if it is causing an unbalanced load. The original overcurrent protection was likely sized at 40 amps to provide protection against overloads and short circuits, but may have been oversized to account for potential voltage drop and inductive load characteristics. By addressing these issues, the current draw can be reduced and the proper operation of the light pole can be ensured. Remember to always follow safe electrical practices and consult with a qualified electrician when working with electrical systems. Consider also the age of the components. HPS lamps and ballast degrade over time. The lamp output decreases and the ballast efficiency also decreases. This means that the ballast draws more current to produce less light. Replacing old lamps and ballasts with new, more efficient models can reduce the overall current draw and improve the lighting performance. LED lighting is now a common replacement for HPS lighting. LED are more energy efficient, have a longer lifespan, and produce less heat. Retrofitting the high mast light pole with LED fixtures can significantly reduce the energy consumption and maintenance costs. When selecting LED fixtures, it's important to consider the light output, color temperature, and beam angle. The light output should be comparable to the original HPS lamps. The color temperature should be chosen based on the desired lighting effect, and the beam angle should be chosen to provide the desired light distribution. Another factor to consider is the control system. A lighting control system can be used to dim the lights during periods of low activity. This can further reduce the energy consumption and extend the lifespan of the lamps. A lighting control system can also be used to schedule the lights to turn on and off at specific times. This can help to reduce light pollution and save energy. Now let's discuss grounding. Proper grounding is essential for safety and for the proper operation of electrical equipment. The grounding system provides a path for fault current to flow back to the source, which allows the overcurrent protection device to trip and to energize the circuit. The grounding system should be installed in accordance with the National Electrical Code, NEC. The NEC specifies the size and type of grounding conductors that are required. It also specifies the methods for bonding the grounding system to the electrical equipment. Another important aspect is surge protection. High mast light poles are often located in exposed areas, which makes them susceptible to lightning strikes and other voltage surges. A surge protection device, SPD, can be used to protect the electrical equipment from damage caused by voltage surges. The SPD should be installed at the service entrance and at each piece of electrical equipment that needs to be protected. The SPD should be sized to handle the expected surge current. Now let's discuss the importance of regular maintenance. Regular maintenance can help to prevent problems and extend the lifespan of the electrical equipment. Maintenance should include inspecting the wiring, connections, and overcurrent protection devices. It should also include cleaning the lamps and fixtures. Any damaged or worn part should be replaced promptly. In addition to the electrical system, the light pole itself should be inspected regularly. The pole should be checked for corrosion, cracks, and other damage. Any necessary repairs should be made promptly. Now let's think about the specific wiring and conduit used in the installation. The type of wiring and conduit used should be suitable for the environment. If the wiring is exposed to sunlight, it should be sunlight resistant. If the wiring is buried underground, it should be direct burial rated. The conduit should be sized properly to accommodate the wiring. The conduit should also be corrosion resistant. If the conduit is buried underground, it should be rigid metal conduit or PVC conduit. Also think about documentation. Complete and accurate documentation is essential for the proper maintenance and repair of the electrical system. The documentation should include a wiring diagram, a list of all the electrical components, and a record of all maintenance and repairs. The documentation should be kept in a safe place and should be readily available to qualified personnel. When troubleshooting electrical problems, it is important to follow a systematic approach. The first step is to gather information. Talk to the people who are using the electrical equipment. Find out what problems they are experiencing. The second step is to inspect the electrical system. Look for any obvious signs of damage or problems. The third step is to test the electrical system. Use a multimeter to measure voltages and currents. Check for continuity and shorts. The fourth step is to analyze the data. Determine the cause of the problem. The fifth step is to repair the problem. Replace any damaged or worn parts. Make sure that all connections are tight and secure. After the repair is complete, test the electrical system to make sure that it is working properly. Document all the steps that were taken to troubleshoot and repair the problem. As a last point, consider energy audits. An energy audit can help to identify opportunities to save energy. The energy audit should include a review of the electrical system, the lighting system, and the heating and cooling system. The energy audit should also include a review of the building envelope. The results of the energy audit can be used to develop a plan to save energy. The plan should include specific recommendations for improvements that can be made. The plan should also include a cost-benefit analysis of each recommendation.